Okay, so I'm going to give you guys a real quick take of some new things that we're doing in the spectrum analysis domain for wideband analysis. I know that with newer 5G standards and a lot of automotive radar and other things, we're doing higher frequency and wider band measurements. Obviously, in the radar and electronic warfare space, we also see needs for this kind of thing. So I had an idea a couple years ago, and with some of the new standards that are coming out, we've tried to employ this to give people a really good idea of some new analysis options that are available from us. So again, I'm going to quickly talk about kind of what the current analysis in a signal analyzer does. We're going to look at some of the moderate bandwidth capability, and then really what I want to talk about is what happens on the kind of the wideband analysis and some of the analog and digital considerations that you may want to take a look at. And then at the end, I'm going to talk a little bit about some of the options to go even further up in frequency, V, W band type of analysis as well. And then we'll take a look at some measurements that we've done. So this is kind of the portfolio of kind of where we see the current signal analysis today. You can see here that current signal analyzer is about 70 to 80 dB dynamic range. We also have internal digitizers that in the modular form factor give you about 600 megahertz and about 75 dBc of dynamic range. Again, this is spur-free dynamic range. And then we do something in the down converter, and this is where I'm going to talk a little bit more about some of the applications here. In the past, it was kind of it was a difficult thing to do with calibrations and the types of measurements that you needed to make. It took some effort to make those types of measurements, and the performance wasn't all that good. But we've had a lot of new technologies we have brought to bear that actually make this a lot better. We also have 62 gigahertz oscilloscopes, and depending upon what your carrier frequency is, you get different performance across that. They're actually pretty linear, both in phase and in amplitude, so it actually does a pretty good job making measurements even in the high frequency space. So we'll talk a little bit about down conversion. This is what I mentioned I primarily want to talk about, and this is kind of the down conversion method that you see in a signal analyzer. You have some sort of front-end amplification. You have a lot of switches in here. New signal analyzers have the ability to kind of bypass some of those lower-end switches, and it gives you a little bit better noise figure, so you get a little bit better signal-to-noise ratio. Most swept-tuned signal analyzers have a YIG filter in it. And so you usually have to bypass that YIG filter depending upon carrier frequency. The higher, of course, you get, that YIG gives you a little bit more bandwidth, but it's typically less than 100 megahertz type of bandwidth that you typically get out of a YIG. So we see that being a band limiter, and so we obviously put a band pass or a bypass around that filter. And then we do mixing different stages for different frequencies. And in one case, I'm going to talk about going out of the IF output, but we also can obviously go into an internal digitizer inside the signal analyzer. So internally, the signal analyzer, Agilent does a couple things. We put a lot of effort into doing characterizations, and our calibrations are, of course, proprietary to us. But we have in this stage here, we actually, after the digitizer, we have an ASIC that does amplitude and phase corrections across the bandwidth. So we do our calibrations, and then we apply those in real time to the ASIC. This is kind of the structure that I was mentioning. So we have an ASIC here, and then we have an FPGA that does, after the digitizer, we obviously have an anti-aliasing filter, then we do digitization. We convert that to an IQ signal. We have our detectors and triggering, so all this is done in real time inside the FPGA. And in addition to that, we have an ASIC that runs in parallel that does resampling and also does that correction I just mentioned. So when you want to do stuff like real-time analysis, this can all be done inside of a bandwidth within 160 megahertz. The problem is when you start to do that above 160 megahertz, able to process these FFTs and able to do the corrections and decimation you need to do, that ASIC and that FPGA can't handle that much data. So this gives a look. We do a very, very good job of performance. I want to pull your attention to the green. This is actually typical performance, meaning we test a bunch of boxes to do it. We're one of the only ones that offer typical. And this is actually not a nominal performance of PXA. This is really what about the average is in the industry. So our typical performance is typically 2 to 3 times better what is currently in the industry. Both amplitude and phase is very good for the PXA, mostly because of three sets of corrections that we do, and our alignment. So you might see quite a few alignments, but both of those things contribute to that kind of performance. So the current idea is we do such a good job internal, why not take that algorithm and apply it to an external? Now that we have external digitizers, we're showing a new scope that we have that has 10 bits of hardware performance, plus we do oversampling, and it really gives you really good signal-to-noise ratio, and it really gives you good flatness performance. So the idea is take those corrections, take that correction ability and put it into the oscilloscope, and now you have a front-end converter that can go into an oscilloscope. So we have some measured corrections that we apply here, and then we also take via, we just link the two via a LAN cable, and we take the correction data out of the signal analyzer. So you're using an external digitizer, but it's using the same kind of algorithm that's used inside of the instrument. So you get that really good flatness and phase performance that you would get from the internal instrument. So this kind of shows the process. Many of you may be familiar with vector signal analysis. So now, rather than doing the decimation and the quadrature detector inside of the FPGA or inside of the ASIC, we're now doing this in a software vector signal analysis platform. And all of the measurement functionality is again inside of the vector signal analysis platform. So we can also do corrections in the same platform. This talks a little bit, I mentioned a little bit about oversampling. Basically, the idea of oversampling is it gives you a reduction in noise. So this has been seen by some of our high dynamic range scopes that have been released the last couple of years. We're doing the same kind of thing inside of the vector signal analysis. And this kind of shows you the performance difference. This shows you some spurs inside of the oscilloscope. This is in the frequency domain, so you got frequency versus amplitude. And you can see that the noise level is reduced, and even the spur level is reduced when you employ this oversampling technique. This is some measurement results on a gigahertz of bandwidth and 500 megahertz of bandwidth for using this new technique that I've been talking about. So you can see basically along this chart, we have about plus or minus 1.5 dB. Down here it's 2 dB. And then in the 500 megahertz, again, it's less than a dB plus or minus on both sides. So it's really good flatness across each band. So this isn't for trade-offs. There are some certain considerations that you definitely want to be concerned about. Obviously temperature. When we're inside of the analyzer, we do a lot of alignments. So we have some internal cal signals that continuously do alignments based on temperature. We also monitor temperature. This kind of technique will not include that. At this point in time, again, there's no cal signal that is applied. This is a pre-done calibration. So there's not an ongoing cal signal, so you'll lose amplitude accuracy versus the gain and attenuation stages. Again, the spurs and residuals in a spectrum analyzer are going to be worse, and one of the reasons, too, is we don't have any aliasing. So you got to watch out for aliasing products. The signal analyzer is banded, so it works somewhat like an anti-aliasing filter, but not completely. And then finally, the processing time. So you're doing this all in software now. Things like real-time analysis, which have been more popular within the signal analysis domain, is not possible anymore. So this shows, this is, I think, a 500 megahertz signal, a 500 megasample signal, I should say. It's a little bit over 500 megahertz of bandwidth. We've been getting EVMs around 3.5%, maybe even a little bit less, across this APSK signal in this case. So it's actually really good dynamic range, the really good residual EVM for performance like that. You can also apply that to something like radar. I think I have an example here where we do chirp linearization, and I have another example if you want to look at the demo in the Agilent booth that shows the ideal signal versus the measured signal in MATLAB with this. So very flat, so it really corrects the flatness. If I showed the other non-corrected version, you would see that you have some distortion from the conversion stages. This is 802.11 AC, and again here we're showing 1.5%. This is probably not as good of a representation of the EVM because OFDM, of course, has correction on its own. So finally, we talk a little bit about that. That solution worked to 50 gigahertz. Now what happens if we want to go above 50 gigahertz? Well, we have external harmonic mixers, and kind of the domain has changed a little bit about how we apply the external mixing from the past kind of legacy, traditional external mixing. We really want to do these types of things. We want to have low conversion loss, minimize our spurious signals, and get the bandwidth that's required across those bands. So this is kind of the traditional 11970 external mixers that we have. The point that I want to make in this slide is there's one thing. You got the IF and the LO on two separate ports, and then we're using, as we go up in frequency, we use a lot higher harmonic number. This, of course, gives you a lot less dynamic range. So we want to try and use a lower harmonic number. Kind of the new method that we've been using now is we actually diplex that. We put the IF and the RF on a single cable. You can see the input comes in here. The nice thing is you can take the mixer to the measurement plane. But we're using a lot lower harmonic number in these cases. This mixer actually has a feedback mechanism. It has an ADC and a DAC inside of it that maximizes the LO power, so you get the correct LO power from the instrument to maximize the performance of the system. And this kind of shows the difference between what we had in the past and what we have now. So this is the newer mixer with the smart technique, with the kind of smarts inside of it, like I said, that actually does auto ranging inside. And then this is the old version. So we get a lot with the lower harmonic number and some of the techniques with the conversion with the LO, where we're actually, we have a control loop inside of the mixer. We're actually getting a lot better performance there. So you can see up to 12 dB performance improvements by using a new mixer technique. This has actually been in some of our legacy analyzers as well, but basically the idea behind this is you shift the LO, and you can algorithmically find out which are images and which one are actually the real signal. So obviously the external mixers do not have a pre-selector, so you have images from the signal analyzer. This shows a performance of EVM at 75 gigahertz. Probably hard for you to see. It's hard for me to see as well. But this shows a performance at 75 gigahertz, and we're demodulating a high-order QAM signal. So we actually have a video on this to encourage you guys to look at it. We also have some demos in the booth that you can come by and take a look at that uses the new external mixing capability. And we have wider band external mixers than we've had in the past, so you can do more bandwidth, down convert that into an analyzer, and use something like the vector signal analysis software to analyze it. Again, we also have some up converters. Again, some of the special ones we have are in the booth that are wideband. We've been targeting things like Y-gig for these types of external mixing and up conversion and down converters. So that was the NASCAR version of the paper. Any questions? If you have any questions, feel free to come to the Agilent booth and we can talk more about it. Thanks.